Alright, homework number 4 on Thermodynamics 1. This is a homework on energy balances, first law analysis of closed systems. And the last problem, problem number 5, is Koretsky's problem 2.40. Okay. So you have a rigid tank is connected to a piston cylinder assembly by a valve, as shown below. Both vessels contain pure water. Okay. They're immersed. Okay, so let's see here. So let's kind of draw this out. Okay, so I have a kind of a tank. There's a valve here, bow tie. This is connected to a piston cylinder. Okay. V1 in here, okay, is equal to 0.1 meters cubed. Okay, I've got water in both. The V total of this tank is equal to 0.5 meters cubed. Okay, the quality is equal to 0.95. This is all being supplied by temperature bath, so the temperature of the system as a whole is 200 degrees Celsius no matter what. Okay. Let's see here. Okay. And my pressure, at least of this, on the surroundings, is 600 kPa. Okay. So this is kind of P external, we'll call it. Okay. Consider the tank's piston cylinder assembly as a system and the constant temperature bath as the surroundings. Okay, initially the valve is closed. Okay, so it's telling you the boundary is basically like this. Okay. So initially the valve is closed. Okay, and both units are in equilibrium with the surroundings, the bath. Okay, the rigid tank contains saturated water with this quality. The piston cylinder assembly initially has a volume of 0.1 meters cubed. The valve is then opened. The water flows into the piston cylinder until equilibrium is obtained. Okay. For this problem, determine the work done, W, by the piston, the change in internal energy of the system, and the heat transfer. Okay, so there's a lot going on here. Okay. But it's still a closed system, first law analysis. Okay, we still have a picture, we still have a boundary. Now, it said to set the boundary this way. Okay. And we're still going to have assumptions. We're still going to assume a closed system. Okay. Because we could draw our boundary right here. But as soon as we do that, it's no longer a closed system, and the math becomes a lot more difficult, or at least a lot more different. I don't know if it becomes more difficult in this case, but it is because we haven't learned it yet. Okay. But it would definitely be tricky. Okay, we're going to assume that delta Ke and delta Pe are approximately 0. Okay, we cannot assume it's adiabatic because, well, it's isothermal, and those are mutually exclusive concepts. You cannot be adiabatic and isothermal, but it is isothermal. Okay, it's not isobaric. It's, the bath is isobaric, but, the pressure that's in here versus the pressure that's on the system as a whole is going to be different. Okay. Now, the pressure on the final pressure of the whole system of both sections is going to be the external pressure because, it maintains that pressure. And so the volume's going to change to common equilibrium. Now, right now, this is in equilibrium, so P1 of the thing has to be equal to 600 kPa. Because this is in mechanical equilibrium before we start. Now, as soon as I add in this mass, though, okay, well, the system as a whole won't have a 600 kPa pressure, so everything needs to equilibrate. Okay. Where am I at? Closed system, okay, I got work. I don't have any shaft work, so no shaft work. Okay. Again, it's not adiabatic, and it's closed system. I think I got everything. Who knows? We'll find out when we start doing stuff. Okay, so let's do our mass balance first. So sum of m dot I minus sum of m dot E, and accent, equals dm dt, control volume. Okay, this goes to 0, this goes to 0 because it's a closed system. So dm dt, control volume, is equal to 0, which means dm is equal to 0, which means m2 minus m1 is equal to 0, which means m2 is equal to m1, which is just going to equal the mass of my system. Okay, but again, my system as a whole. Now, if we did draw the boundary here, this math would be a whole lot more complicated because I'd have mass coming into one, I'd have mass coming in out of the other, there'd be a change in time, and all these goofy things going on, and I don't know, and blah, blah, blah. Okay. So, we have now our energy balance ends, m dot I h I plus 1/2 v squiggly squared I plus g z I minus exits m dot e h e plus 1/2 v squiggly squared e plus g z e plus q dot plus work dot equals d u plus e k plus e p d time control volume. That goes to 0 because, and that goes to 0 because there's no change in kinetic energy or potential energy. There is work, there is heat, there's nothing coming in, and there's nothing coming out. Okay, so I have q dot plus work dot equals d capital U dt of the control volume. Okay, I'm going to bring that down here. Okay, well, the pressure in this system for the piston is actually the same. It's just the volume is not. So we do have to say that the connection volume, connection V, is negligible. Okay, because we are going to have a change in volume. We're going to go from basically, just V1, to V1 plus V tank. So that's kind of our V2 of our system, basically. It's going to be V1 plus V tank. Okay. Because we're going to assume that that valve has negligible volume attached to it. Okay. Let's see, or at least it's accounted for in that half a meter cubed. Okay, and so I have, and I'm trying, well, what am I trying to find out? Okay, I'm trying to find a bunch of things. I'm trying to find the heat transfer, the work done, and the change in internal energy. Well, first off, let's do the work done. The work done is going to be minus PdV. Okay. V1 to V2. Okay, so that's, and again, this is, my pressure's constant, so my work is going to equal minus P, or P of V1 minus V2, but V2 is equal to that, so work is going to be basically P of V1 minus V1 minus V total. Okay, and so my work is going to basically be minus V times the V of the tank. Okay, because that's how much it's going to expand it by. Okay. And the pressure's that, the V is that, so I have my work, okay? But basically it's going to be equal to minus PVT, okay? So there's my work, okay? It also wants to know what delta U is going to be. Oh, well, delta U is, again, pretty straightforward. Okay, so delta U, for a thing is just going to be U2 minus U1. So I get these from looking at the different states for water. So if I do that, okay, so it's isothermal, right? Yeah. So, but I remember the temperature because they erased it on this. And the temperature is 200 degrees Celsius. Okay, I was right. Okay, so I have. Well, the specific change in energy is going to be the same. Oh, well, no, because, no, well, let's see here. Yeah. Well, let's see here. Okay, because that's going to have a certain amount of pressure to it. Okay. But as soon as this is going to be some pressure, it's going to increase the pressure and maintain the whole pressure of the system. So yeah, I mean, the pressure is constant in this case. Okay. And the pressure is going to equal 600 kPa when we're said and done. It doesn't really matter the quality other than it's going to tell us the mass. That's what it's going to tell us. It's going to tell us the mass of what we start with. Because we know the temperature, we know the pressure, and so we need to get the specific volume at this case. The specific volume doesn't change, but the mass is what's really changing here. So the change in now, so if the problem asks for a change in total energy, okay, well that would basically be, well, that still would be, because it's the same temperature, it's the same pressure. There is no change in energy. It can't have a change in energy because the pressure and the temperature do not change. Well, I guess the pressure of this one is different. The pressure of the whole system is different. Okay. So there would be a change in internal energy. So what I would need to do is, I basically have, kind of M of the tank of, U2 minus U1 plus M of the cylinder, U2 minus U1. Now the U1s are different, so this one would be the cylinder, this one would be the tank. The U2s are the same because that's going to be, at P equals 600 kPa. Well, really, the mass, this one is 0 because the mass and the pressure and the temperature are the same. So this one is 0. Okay, it's this one that's really the change. And that one I can get from, so I can get, at P equals this, T equals this, to 200 degrees Celsius, that's going to be U2. My mass total I can get from my initial condition or whatever, and so that's at, B whatever is going to be equal to 0.5 meters cubed. Do I have a mass? I don't have a mass. Okay. But I do have, a volume, I do have a quality, I do have a temperature. So really that's what it is. I have a temperature and a quality. So it's not this. I have at 200 degrees Celsius and x equals 0.95. I can get what the specific volume is, and then that I can get from my, I can get my mass in my tank. Okay. Because that's going to give me my mass in my tank, and it's also going to give me my U1 of my tank. U1. Okay. Because I know my total volume of that tank. Okay. And then the last thing is saying how much heat. Well, this is just kind of finishing out the energy balance up here. So if I kind of simplify this down, I take away my time. Okay, I've calculated what du is going to be. I've calculated what work is going to be. So basically, Q is equal to du minus work. But I calculated those at this point, so I could just calculate what Q is at this point.